This is Team 1086, and we solve problem C, dog cannot catch. Our names are Ryan, Aahana, and Aarushi, and we're from the Illinois Mathematics and Science Academy, and our team coach is Dr. Cho. After watching the YouTube video provided of Fritz the dog, our objective is to create a math model of the different object trajectories given to the dog. Questions for us to consider include understanding the behavior of the dog and trajectory of different objects.
We considered two dimensions which are x, horizontal, and z, vertical. So our approach to the mathematical model was that we had some input, namely the vertical distance of the owner and the dog, the initial velocity at which the food was thrown, the initial angle, and the shape and weight of the food. We needed that input to go through the model and give us the trajectory of the thrown food, the total time, distance, and the final angle of food. We also factored in the air drag resistance in the thrown trajectory. We calculated this using the conservation of momentum equation. We represent acceleration and velocity as a vector in order to understand both dimensions of x and z. In this equation, we use mass times gravity to represent the gravitational force on the object, and we also did cv squared, where c represents the air drag constant. The air drag constant includes the drag coefficient, density of air, and also the cross-sectional area. The cross-sectional area is based on the food's diameter at that certain moment in time. For a visual representation of this, you can see in the image on the right that objects with a smaller diameter at that moment have less air drag resistance. But as the diameter increases, so does the air drag resistance. To create a math model, we solved the equation of motion described in the previous slide in the x direction. First, we found the velocity in x direction versus time, and since gravity is 0 in the x direction, there is no gravity in this equation. Then substituting terminal velocity that we calculated to be the root of mg by c, and we integrated both sides of the equations, and our final equation is this in the yellow box. We also wanted to calculate the velocity versus distance in the x direction. Our initial equation is the same as the second equation used to find velocity versus time equation. We used chain rule and then integrated both parts to find the final equation in the yellow box. Then we moved on to find the equation for distance versus time. This we found easily by integrating the first equation of velocity versus time to find the final equation in the yellow box. Similarly, we solved the equation of motion in the z direction. The first one was velocity versus time, but this time there was gravity facing downwards that we had to account for. However, the rest of the process was very alike, and after substituting terminal velocity, integrating both sides of the equation, we found the final equation to be that in the yellow box. We also wanted to calculate the velocity versus distance for the z component. Our initial equation is the same as the second equation used to find velocity versus time equation. We used chain rule and then integrated both parts to find the final equation in the yellow box. Then we moved on to find the equation for distance versus time. This we found easily by integrating the first equation of velocity versus time to find the final equation in the yellow box.
Using the concept of conservation and momentum, we calculated a list of differential equations. From these differential equations, we then found analytical solutions to use in our mathematical model during our Python code simulation. We can see the different effects between different objects shown in the YouTube video of Fritz the dog. Different orientations affected the terminal velocity as well, as we can see a distinct difference in terminal velocity between the donut horizontal and vertical orientations. Overall, small object geometries and large cross-section areas created slow terminal velocities the most.
Based on the data that we have just seen, the graph here shows the effect of the drag constant on the food in a certain orientation with respect to horizontal distance. All of the foods were thrown from the same vertical height of 1.5 meters. The x-axis is the horizontal distance in meters, and the vertical distance is represented by the y-axis. Additionally, the graph on the right shows the time, distance, and angle with respect to the terminal velocity. As I explained before, the shape and orientation of the food matters as it affects the horizontal distance, travel time, and the final receiving angle. As we can see, the shape of the foods changed significantly from the time it is thrown and the time it reaches a dog. And this is what makes the dog confused, as they do not understand the trajectory of the food. So to answer our first question of whether certain foods are more difficult to catch, we think yes, definitely. This is because the terminal velocity is affected by the mass and drag constant, which in turn is affected by the cross-sectional area, as we can see in the equation. To take another example, the pizza on the right shows the different diameters, and this will hence affect the air resistance and the cross-sectional area. The angle at which the food sample was thrown factored into the travel time, the distance traveled, and the final angle. On the left side, we graph the effect of throwing angle on the trajectory of the food sample. Here, the y-axis shows the height at which the food sample was thrown, which is constant in this graph at 1.5 meters. The x-axis represents the horizontal distance the food travels from the owner. The travel time on the right increases as the initial angle increases. However, the maximum travel distance occurs at 22.5 degrees and decreases until it reaches zero when the initial angle is 90 degrees. The final angle at which the food reaches its destination decreases as the initial angle increases. The initial velocity at which the food sample was thrown also had impact on the final trajectory. We graph the effect of throwing speed on the trajectory of the food sample, and we can see that as the initial velocity increased, so did the horizontal distance. The travel time, travel distance, as well as the final angle increases as the initial velocity increases.
The initial height also affects the overall displacement as seen from the graph on the left. We can also see that as initial height increases, so does the travel time. This connects to our results in the previous slide, answering question 2 as yes, the height at which the object is thrown does matter since it changes the overall horizontal distance. Question 3. The dog will have time to orient his head once the trajectory leaves its maximum height. We can see that in the graph in the left that only after the maximum vertical distance is met, the horizontal displacement is understood. The initial angle of the trajectory also supports our answer by showing that even if the initial angle is high, such as 67.5 degrees, it could still end up being a shorter horizontal displacement than shorter angles like 45 degrees.
Question 4. Perception-wise, the dog needs to understand the weight and size of the object, which can be roughly understood from the terminal velocity of the object during its trajectory. It also should perceive when the object drops from its maximum trajectory, allowing it to maximize its time to relocate itself into the correct position. Behavior-wise, we notice that Fritz constantly moves its mouth away from the object's landing position when it was right in front of it. So understanding the relative position of the object when moving its mouth, which blocks its eye of viewing, is important. It should also have a very fast speed to maximize reaching the thrown object's final location on time. Question 5. Is Fritz clumsy or is the owner being mean? Our answer is that the owner is being mean. This is due to many factors that include how the orientation of asymmetrical food samples change during trajectory, confusing the dog and affecting the object's air drag force, which affects the object's velocity, and the changing weights of the food samples, which makes it hard for Fritz to adapt and predict the trajectory. To expand on the changing orientation, this picture shows that if the dog saw the front view of the food sample but saw a different view when it was about to catch it, it might have confused Fritz, thus changing his move last minute. But what if the owner unintentionally confused the dog with the constantly changing cross-sectional area of the object being thrown? If we focus on the strawberry and the meatball that we assume to be both spherical and symmetrical, we saw that Fritz couldn't catch these food samples. This supports the fact that the owner is mean and purposefully confusing the dog through different weights and sizes.
Question 6. The dog should stand on the spot where the food falls within the radii of the length of the dog's head so that even if the predicted trajectory is a little off, the dog can still shift its head in the last moment to catch it. So in case of the predicted trajectory is off, a dog with a larger head will have more likelihood of catching it because that's a smaller standard error. Question 7. As stated in question 5, we believe the owner is exploiting Fritz for more money. We believe that by throwing deformed objects and throwing multiple different object weights at the dog will never be able to properly predict the front view of the object since it constantly changes in patterns and the different weights can attribute to different terminal velocities affected by air drag.